the channel with time introduction. Good morning, ladies and gentlemen. Today, I'd like to talk about tactile image sensor for detection of surface friction and hardness. When a human touches unknown object, he can get tactile information from his fingertip. He thinks where the object is, rough or smooth, hard or soft, hot or cold, and dry or wet. Based on the comprehensive evaluation of these tactile information, the human finally finds out the object materials such as metal, paper, plant, or animal. If a tactile sensor device can get this tactile information, we can distinguish the difference of target object more precisely. In this study, we propose a new tactile image sensor for detection of hardness and friction using the reference plane structure. In this device, silicon microdiaphragms are formed on silicon tip, and piezo-resistive detection circuit are integrated on each silicon diaphragm structure. On the silicon tip, contact tip structures and the reference plane, which is the baseline of position detection of the tips. At the initial condition, silicon diaphragms are swollen by air pressure applied from the device backside. This device structure have detection ability of frictional coefficient and the surface hardness of the touching object. In the next slide, I will explain the sensing principles of two kinds of tactile information using the cross-sectional view. First, I will explain the detection principle of three-axis force with contact tip structure and piezo-resistive stress sensors. If a vertical load or horizontal load is applied to the contact tip structure from the touching object, components of the input force are individually detected by the piezo-resistive detection circuit. Utilizing the detection ability of three-axis force and the reference plane structure formed around the contact tips, the friction coefficient of the surface can be detected easily with the new tactile sensor device. The function of the reference plane is very important, since the vertical load applied to the tip structures can be limited by the offset of the contact tip from the plane. Since the normal force Fg is known value, the friction coefficient can be simply calculated by measuring shear force Fx. Next, I will explain the principle of surface hardness detection. The reference plane structure has also important role in this measurement of hardness. If the device surface contacts to the target object, the indentation depth of the contact tip to the object depends on surface hardness of the object. So, we can measure the hardness with the position of the contact tip from the reference plane head. Since indentation depth from the reference plane is only dependent on the surface hardness, this hardness measurement is almost insensitive to the surface applied force on the tactile sensor device. Therefore, surface hardness is very easily obtained by the proposed tactile sensor with the reference plane. Next, I move on the device design. This is CAD layout design of the tactile sensor device in this study. The tip size is 5 by 10 square millimeter, and 4 by 4 pixel array circuits are integrated on the silicon diaphragm array. The pixel pitch is 820 micron. This figure shows the detection circuit of single pixel structure. In each pixel, the contact tip structure is formed with SU8 layer at the center of the circular diaphragm. The reference plane structure is also formed around the diaphragm in the sensing pixel array region. Piezoresistors in the pixel are laid around the tip structure, and they correspond to the colored resistors in the 3-axis force detection circuit. From the 3-axis output, friction coefficient and surface hardness can be extracted according to the principles. In the next slide, I will discuss the fabrication process of this device. Starting material of this tactile sensor device is an SOI wafer. First of all, the detection circuit is fabricated by standard integrated circuit technology. Then, the silicon diaphragm array is formed in the handle layer by deep reactive ion etching process. Finally, the reference plane and contact tip structures are formed by 76 micron thick SU8 layer with single lithography step. The fabricated wafer was diced and packaged on printed circuit board for tactile sensing evaluation. This photograph shows a fabricated tactile image sensor tip. Sensor array is integrated around this area, and the wiring pads are laid far from the sensing array region in order to prevent damage of the bonding wires. This figure shows 3-dimensional surface shape of a pixel structure by white-light interferometer. The reference plane and contact tip structure with 76 micron height formed on the pixel integrated circuit. This same photograph shows sensor surface and backside of the sensor array region. The reference plane structure and contact tip structure are formed on the tip surface as shown in this figure. Circular shaped silicon diaphragms are precisely formed as designed in this. 3-axis force detection ability of the tactile image sensor was evaluated. This figure shows a measured G-axis output dependence on the applied normal force to the contact tip. The normal force sensitivity was 0.07 mV per millinewton. On the other hand, the shear force sensitivity was 0.73 mV per millinewton. As we can see, horizontal axis force sensitivity is around 10 times higher than the vertical axis force sensitivity. Therefore, small friction coefficient around 0.3 to 0.1 will be detected with this new device. In this slide, I explain the result of real-time frictional force detection with the implemented device. Frictional force with different direction was applied to the device surface as shown in this animation. The object was repeatedly moved in the 2 directions, and the output signal of the frictional force was recorded as plotted in this figure. The detection ability of frictional force of the tactile image sensor have been successfully demonstrated. Finally, hardness detection ability of this device was evaluated using 3 kinds of samples with different materials. In this study, SHOA-A hardness is employed as a unit of hardness measurement. First, the function of the reference plane on hardness measurement was confirmed. This figure shows the output output voltage dependence on the contact force for various measuring objects with various hardness. As we can see, output dependence on the contact force is small enough to distinguish the hardness difference. This small dependence is realized by the proposed reference plane structure in this study. From the result, we can plot output dependence on shear A hardness of this tactile sensor as shown in this figure. The relationship between the measured output and shear A hardness of the samples is very close to linear line in the range from 22 to 99 HS. The softer material with 22 HS is a memory foam, and the middle range hardness samples are erasers. The hardest sample is final plastic. Finally, I'd like to conclude my talk. Multifunctional tactile image sensor with the reference plane structure has been newly proposed, fabricated, and evaluated. 3-axis force components were successfully detected and frictional force was measured. Finally, detection ability of shear A hardness was successfully demonstrated. Thank you very much for your kind attention.
The floor is open for